talk about that, but that's actually a big problem for a lot of people. And how many people walk around with an iPad and access their data? That's a big issue, right? This is the one that surprises me the most, is DR and DC being down here at the bottom. Because we always get engaged in that conversation every time we work with one of our IT clients. So we're very surprised by this. But we're going to talk today primarily focusing on this consolidation and optimization. And I'm going to talk about some new technologies and things that are going on that are going to have impacts in the industry. First one is optimization is about how do you bring solid state into IT. This is probably the number one thing we get engaged with our IT clients is how do we do this? How do we bring it in here and optimize our environment with solid state? And how do we do it within the financial constraints of what we have? This is probably the biggest issue with everyone is trying to get them to understand it's a different economic model. You have to think differently when you start talking about solid state. Biggest problem is trying to get that conversation to get them off of the way they've been thinking and say it's a different way to think now. A little bit on solid state. Solid state's just non-volatile memory. Keep that in mind. There's an awful lot of people that focus the world on a particular implementation. What we're talking about most today is NAND flash technology, or flash simply, but it's really non-volatile is where the industry needs to focus on, because there will be different technologies that come along. You need to look and say this is a long-term issue. Today we looked and we've been doing DRAM with batteries, DRAMs with supercaps. The newest thing coming along next is phase change memory. Phase change memory will be here and be economical in about 3 years. It's going to just continue on with what we've got. So an investment in non-volatile memories today will be exactly what we want to do and have a long lifespan. The big deal is we're getting rid of electromechanical devices. Things that we have to wait to rotate, wait for an actuator to go in and out, and things that wear out, produce heat, and require cooling. Obviously, they're a whole lot faster. Electronic access speeds now, it really does change things. What we're going to look at is how this is being adapted currently and some of the things that are happening in the future. This is what we get to, and we talk about a lot, this is an inflection point in the industry. This changes everything from this point forward. This is very important to understand. We're going to remember this point coming out and saying in the year of 2012 and 2013, we started seeing all solid state systems, IBM flash systems, for example, that came in, we started using them, and everything was different from this point forward. That's how important this is. We can all remember big changes that happened in the industry. The first time you started getting access to an internet website. The first time you started doing emails. All those things were inflection points. Things changed. This is another one of those examples. So the real crux of it is we've had, over time, this diverging line here of servers and processors going faster, more capabilities, more processor cores, more processors in servers, getting a lot more work done. Meanwhile, we've seen basically almost no change in the last 15 years with disk-based systems. Being held back by the electromechanical motions. Spinning them faster, 15,000 RPM seems to be about the limit when things start to fly apart, literally. Actuators, actuator motors, all that stuff has changed, has not changed in a long time. Now we're dealing with electronic speeds, and we can close that gap. Now, one of the biggest things that have happened in the last 4 or 5 years has been multi-core processors. Multi-core processors have brought in excess capacity from what we could do originally, and then we started putting virtual machines into our server systems to use that capacity. It actually exacerbated the problem of where the storage was. So that gap became even more critical. Now we're dealing with some solid state that's going to bring in capabilities to do more with those processors enabled by solid state. The other thing that we've done, and those of us that have been in the design industry for a long time, we've done a lot of unnatural things trying to compensate for that problem with disk drives effectively. We've done a lot of things like distributing data very wide, lots of places. We've done a lot of things to put a lot of algorithms to try and hide the electromechanical motion. It added tremendous complexity and a lot of failures into the system. We put things in like RAID protection in the failure mechanisms of the disk drives. And we tried to do some unusual things with striping data and things like that, adding a lot more complexity. It made it more difficult to find problems. It created some other problems with performance if we didn't do it right. When we start looking at what solid state's going to bring to us, we can simplify it, remove some of those complexities. So give you a little perspective on what this difference has made in a couple decades. You can see that the storage industry has been a laggard in keeping up with the rest of the technology advances. It wasn't until I really looked at this chart and looked at those numbers that say how far behind it really was. It was falling further and further behind. And so then you say, well, wait, I've got these high capacity disks, and I've got 2.5-inch disks now that will spin at 10,000 RPMs. I'm going, it's an incidental improvement compared to the other improvements we've seen come along, specifically in processors. I didn't realize how big it was until I looked at the magnitude. This 20 years, almost 3,000 times improvement. It's incredible. So I've been in the storage industry way too long, at least my wife tells me that. And it's almost embarrassing saying we've only had a 25 times improvement in those 20 years. Okay, so we put this chart together to talk about where solid state is most appropriate. And I'm going to tell you a few things here that make a lot of sense. Where we're at today, we're in the early stages of solid state technology. We've got some pretty fantastic products out, and there are going to be more. But you look and say, where can I get the most value? Well, I've got capacity and on the chart here against performance requirements. The greatest value people see today from the systems come out have to do with performance. Also, you look at it and say, well, it might be a little expensive, so I want to go after the greatest performance advances with the least capacity demands. So that's going to be up and to the right, and that's going to be transaction processing. It's going to be my virtual infrastructure environments, and that's where I'm going to get the most benefit for my investment. Well, what about all the other things? Do they have value? Absolutely. And the big point I'm going to make is we're making a lot of technology changes. High performance computing environment, those environments typically, they'll pay any amount of money to go just a little bit faster. So those are great sales opportunities for most people. Online archive. Archiving we're going to talk a little bit about later, but it's one of the very fast-growing areas of opportunity. There's some new applications of flash technology coming out that have what's called life amplification. And you're going to see flash come out that has 15 to 20-year lifespans to use in that environment. Now, if you start doing TCO calculations, if I can keep something on a technology for that period of time, it's very, very valuable. Not available yet, but that's one of the new applications coming out with flash technology. So the biggest one that we've seen, database acceleration, going after the tier 1 applications to make them run faster. That seems to be contrary to what a lot of people think about and saying, well, wait a minute, I need lots of data. And the answer is actually not. If you look at the majority of the databases out there, they're actually very small. The average size of a database, average size, is somewhere around 500 gigabytes. Isn't that amazing? They're pretty small. So if I can put that entire database into a solid state, think about how much faster it's going to run. I'll give you an example of one of our customers I went through this with and what the results were as we go through this. Another one is this problem with server virtualization. Server virtualization, I'm going to use all that processing power, all those multi-core processors that I have, and put more VMs up there. I'm going to run those virtual machines with multiple operating systems and applications. What have I done? I have created an I/O blender, and so storage systems that we design with heuristics in them to try and look for patterns of sequentiality, totally destroyed. Because I've got an I/O blender going on, and all my I/Os become random to the storage system. Worst possible thing could happen. I've created an artificial, or real, actually, bottleneck to the storage to support all those VMs. If I can now get rid of delays for mechanical motion, I can service more VMs. This is a simple measure, and people look at it and say, I can put a solid state technology in, a flash system in, and I can instantly double or triple the number of VMs per physical server. What's that worth to me? Because I relieved that I/O bottleneck. Same way with virtual desktop infrastructure. There's a lot of you probably have projects or want to move towards VDI environments. How many desktops can I support? And it turns out the virtual desktops is a worse problem than the number of VMs per physical server. It's a much worse problem. It's like multiplying it by 100 times. Because can I get 500 desktops on that physical server versus 50 virtual machines? So this is another way to deal with getting more out of my storage systems, and that's applying a solid state technology to it. And how many here are big data analytics environments? A few of you. One of the things that's been real interesting is we've been seeing a lot of people that deploy Hadoop environments, which typically use one-use servers with captive storage in it. They're putting in SSDs into that captive storage. They're not using spinning disk at all. And they're finding that these environments, maybe with 1,000 one-use servers, each with 2 SSDs in them, can dramatically accelerate their time to results. And the whole thing about this analytics is how fast can I get my answer? So this is a big movement underway, is to move away from spinning disk in those servers. And they're getting inexpensive enough that we're seeing a lot of people do this. Here's another example, is in a cloud storage provider. And this is one from Cloud Sigma, who has 2 main sites. One's in the Las Vegas Super Center, and the other one's in Zurich. What they found is that they used one-use servers with 4 spinning disks in them, and they swapped out their spinning disk and put 4 SSDs in them, and they could instantly increase their number of customers by 3 times. And because they were not spending a lot of the CPU time waiting on I/O to complete, they could reduce the CPU utilization and the amount of time memory was locked waiting for the I/O to complete by about 25%. They said when they put and swapped out their 4 spinning disk for 4 SSDs in all those servers, said the payback was instantaneous. That on paper, it didn't make sense. As soon as they did it, and they did a POC, but they did a very small one, and they just went ahead and did the whole thing. And it was instant payback. They also use data reduction because they do a lot of hosting, both of Windows and Linux-based operating systems. And they found the data reduction, they were capable of ramping it up to 8x because of the performance they had, that they could do that transparently to the customer. That's pretty interesting. So this is a real world example. I spent some time with the CEO of the company. He lives in Slovenia, of all places, and I never figured this out. Why he lives in Slovenia and has data centers in Zurich in the US. But he was explaining to me that they calculated this out on paper. They didn't believe it. They did a proof of concept, saw it, and they just went complete all in on this, and it was a big payout. So what we're seeing solid state entering into areas that we originally didn't think would be that interesting. This is an interesting one, and to get the reference to the picture. In a high-performance computing environment, we deal a lot with some of our research firms. And the biggest one we've seen that's been excited about doing this is with genomic research. There's a lot of pay-for-analysis companies now where they will do sequencing for you. And it's a real-time, get it back as soon as possible. Not just from law enforcement, but these are people primarily doing it from figuring out whether they have propensity for a particular type of disease or something. They're finding that their results are so much aided. Rather than taking maybe 3 days, they can turn this around in an hour with using solid state technology. So I put this chart together, and this really helps when I talk with our IT clients. Okay, so what types of things do we have today? So let's talk below the line here. I can add flash into an existing storage system and use it for caching. What I'm doing there is adding more cache capacity, which was previously just DRAM, by using less expensive flash. And I may do some tiering between DRAM and flash, but I can greatly aid the performance by having more data in cache. Now remember, if I'm caching data, I'm also paying for that data to have another home somewhere else, on spinning disk or in SSD somewhere else. So I'm paying for it in 2 locations, but I can greatly aid performance by having a cache area. But again, it's an additive cost. Another thing we're seeing a lot of existing storage systems, the ones that were designed for spinning disk, is to put a tier of flash in. The majority of these are using SSDs that are designed to mimic spinning disk drives with the protocol like a SCSI protocol and connectivity, maybe a SAS connectivity. So they're trying to mimic a spinning disk so it's easy to insert into those environments and then add software to manage movement of data, the higher access data to be on SSDs and lower access data to be on HDDs, to move data internally. And that's a dynamic tiering, and there's a lot of different vendors that use different names for this. Easy Tier is the IBM name that you might hear. EMC uses Fast, a lot of different names. Dynamic tiering. What we typically see here, and we've got a lot of data to support this, that if you put SSDs in, you typically max out the performance of that storage system with about 4 or 5% of the capacity in SSDs. After that, you get no more performance out of the system. We also find that those systems with SSDs in them will give you about 2x the performance compared to having all HDDs. There is a change. If you get a system where it's been, the internal code, the microcode of the system has been modified or optimized to look at using flash first. And this has to do with changing with the queue depths, changing with the number of threads that are started, the processing. So the original design that was built around optimizing for overlap of mechanical motion is changed to not do that. You can get 4 to 5 times the performance out of those systems. So that's what you're going to get out of those systems that are mixing spinning disk and HDD. It's about 5x of performance when they have the code optimized. And then we see some vendors that haven't done too much yet. They just take a system and throw all SSDs in there and say it's an all-flash system. Those were not designed for flash, they just populated only. And most of the time they're a static assignment, so that there's no tearing or movement. More expensive solution. Then we have systems that are all new designs. They were designed initially for solid state. They were designed either for DRAM or for flash or some other type of solid state technology. That means that everything was optimized around the fact that it can get instantaneous response and I don't need to worry about electromechanical motion. Those systems typically come out with what we would say, compared to an HDD-based system, about 10 times the performance. And you normally hear vendors marketing talk about 1 million IOPS type of systems. Well, that's a bit misleading, and we're going to talk about that in a minute. But these are significantly greater performance than a system that was designed for spinning disk. Now, we also have a lot of flash PCIe cards out there. And what you're doing is taking NAND flash systems on a card plugged into a PCIe slot in the server. That is used in a couple different contexts. It can either be used as a virtual disk drive. It can be used as a caching area. The problem with plugging it into the server is that it's no longer a shared resource. Not being a shared resource means it's local to that server. I've got business continuance issues, DR issues, and so the only way you can make that a shared resource is to add another layer of software that will communicate over a network to other servers to mirror data and manage what's in there. It's another bit of overhead, another bit of complexity, but it does work very well and it accelerates performance. So you've seen a lot of people do that today. And most of the time they do that, they do it in concert with another implementation for the larger shared storage environment. Now, what's going on here is we've got primarily Intel, but a couple other vendors are also changing this out. And they're saying, rather than plugging a card on the PCIe bus, which has a bottleneck to go to the access and number of things that plug into the PCIe bus, let's change this and let's make flash directly accessible on the memory bus. On the memory bus, think of it, let's take a simple example. It's not going to be like this, but it's real simple. Let's say rather than plugging these DIMM cards with DRAM into sockets on memory, let's say I only plugged in so many of those of DRAM, and I plugged in all the rest of them were flash. I've got persistent memory then, very important, persistent memory at an order of magnitude less cost, not quite the same performance. But that's what, in general, what's going on here. And we'll start seeing that probably late next year. That changes things a lot. All of a sudden now we're not going to be talking about buying a server with populating so much DRAM. We're going to talk about buying a server with so much DRAM and so much flash in it. A little more complicated. And then I'm still going to need that layer of software in there to manage a shared resource. So this is probably late next year. It'll be commonly available. And you're going to hear a lot of names, trade names, brand names around the different solutions for this because there's more than one vendor here. So integrating solid state into the environments, yeah, we've seen a lot of this. This is what we see a lot, caching here, and a good example is NetApp. That's what they do, is you plug in different cards and operate as cache. EMC has flash cache, no, what do we call it? Fast cache. There's a whole lot of different solutions here. And what you're doing here is this is cheaper than DRAM. That's what that's all about. Dynamic tiering, much more sophisticated, movement of data, very effective performance. Again, 2 to 5x the performance out of this system, depending on the implementation. Very effective. And then you've got all solid state systems, which are much, much faster at this point. So a little bit on technology. Today we're primarily focused on NAND flash technology. And there are 3 versions out there. There's single level cell, multi-level cell, and now there's triple level cell out. Single level cell says, in the substrate I have a well, a location where I can store a charge. And I can read that charge, whether it's there or not, and that'll give me a 1 or a 0. Multi-level cell says I can store a charge in a well, and then I can read the intensity of the charge. And the intensity then can be encoded to give me more bits, 4 bits basically, for that location. Triple level cell says I've got finer granularity on reading that charge, so now I can get 8 bits from the single cell. Obviously, each one of these represents a different problem in production, and it's all about the lithography process and using and producing that cell. That continues to get better, and typically we see a doubling of that process that occurs on about a 12-month cycle. So about every 12 months it gets an order, a complete doubling of what goes on. NAND flash in these environments typically has about a 7 to 10 year lifespan in an unpowered state, except for EMLC, and that's a little bit shorter because of the way they do their erase cycles. The other thing people worry about is saying, well, wait a minute, I heard about wear out, and there is a problem. What wear out is, in these cases here, is as I write to these locations, one of the big issues with flash and why it's so inexpensive, as opposed to a design like DRAM, is I don't individually provide all the circuitry to be able to write and erase every location. To make it cheap, I'm able to read every location, but if I'm going to erase it, I have to erase an entire page, which may be like 8K. So that's to make it so it's cheap and compact. And that was one of the design trade-offs. So if I'm going to erase this, what I have to do then is basically do an overvoltage, and when I do that, I erode a little bit of that insulation. And that erosion plugs up where I read the data. Now, remember I talked about life amplification that's going on with some of this technology? Well, they've come up with a process here to do a back bias through there to basically blow out the debris that's causing it the problem, and they can basically double or triple the life of it. That's what you're going to see shortly. But this wear out has manifested itself saying that I can have maybe 100,000 writes with SLC and 50,000 writes with MLC or something like that. What's gone on now is we've seen a thing called wear leveling, where all this is memory mapped, so I can wear things out on about an equal basis. They also have sparing. And in most of the MLC devices, you may see up to 50% of the cells actually be there as spares. And so most of the guarantees you'll get from this technology is a 5 or a 7 or a 10-year lifespan. Do you care if they guarantee 7 years of life about wear out? Not really. What we've seen is a lot of the marketing presented about this is for people who don't really have a good control of that today. So the other thing we're starting to see is data reduction. These being very fast, we're seeing a lot of vendors starting to implement data reduction right in the flash controller, so it's totally transparent to the outside world. And what we're seeing is about 5 to 6x reduction in data. It changes the economics dramatically. So that's one of the things you're going to see. That's why when we get the 6x reduction today on some of that, the lifespan issues and everything, it's really not an economic difference with HDD. We'll talk more about that in a minute. So, very valuable, about a quarter of the power, about 6x the basic reliability. Don't have, if you got 1,000 disk drives, you don't have people running around replacing them all the time. One of the things we're starting to see is this becoming a competitive issue between vendors. Rather than it's coming out saying it's got a 3-year warranty, 4-year, or 5-year, we even got one out there, a startup company guaranteeing a 10-year warranty on these systems. It's going to be a very competitive issue, and the reason it's different is the wear-out mechanisms are different. Cost decline, absolutely. There's going to be new generations, all great stuff. The big thing is, from an IT perspective, is you start to think about the tier 1 applications, the virtualization environments, starting using that where it makes sense today, and then going to move beyond that in the future. Now, the IBM Flag system, which you've got Chris over here talking about, is a great example of that. 24 terabytes in the one you know. I don't know of any databases that have their core operation that's greater than 24 terabytes. They come out with a 3-year warranty, and the big thing is it was designed from the ground up as an all-solid state system. So they'll talk to you more about that over there. I don't need to go into this. But this is a great example that's being very, very successfully deployed. So what do you expect? Well, 2 to 5x performance if you just put solid state into an existing system. Basically 10x with a new design, less fine tuning. That's a big one. I'm not going to have to keep going around trying to chase a lot of details and move data around to balance it. Response times, we're dealing with really sub 100 microseconds for most cases. And you're going to see this, the big issue is what you get out of the REST system. It's an enabler, and that's just where the equation is going to change, and that's what I'm going to go into next. I'm going to see a reduction in the dollars per IOP here. I'm going to see greater consolidation, greater VM density, faster transactions, and in this analytics area, faster results. Reliability, obviously, no ongoing disk failures and replacements. All of these systems have been designed to do a constant integrity verification and remapping of cells. So they've started off this process much better, whereas most of these are grafted on the spinning disk. Lifespan, you're going to see that change. And this is the big one, is over-provisioning goes away. This idea of short-stroking disks to get more performance out of it is a big deal. So let's go through how you think about this now. The economic measures are different. How many of us still think about storage as $1 per gigabyte? Ah, you're afraid to admit it. We're going to talk about that. The value then comes not really from reducing the cost, but it's getting more out of the entire environment. I get more value out of everything else I've invested in. More value out of that server because I get more out of it. More value for the application. And a lot of these applications I'm paying for on an ongoing basis, and my investment is sunk there. If I can get twice as much I/O out of that, twice as much work done out of that, it's more value. Now, so it's all about this. Now, the simple measure is dollars per IOP, but that is misleading. Now, I'll show you why in a second, but it's very misleading. But it's what we gravitate to today, saying, oh, if I go to a solid state system, I can get 10 times the number of IOPS. If I go to 10 times the number of IOPS for this amount of money, I can now do the math, relatively simple math, and says, what does $1 per IOP cost? And that works out fairly well. But it's really not that. It's the effect on the entire system that I have to measure. So here's the example I went through with a particular customer. In this case here, their biggest thing was they wanted to get 1,000 more transactions per second out of this application. That particular thing was using a database, and on average, to complete a transaction was about 8 disk IOs. The problem that they had was application IO dependencies. What that meant was every time I wanted to do a transaction, I would do an CPU execution was, in this case, about 100 microseconds. And then I would do 5 milliseconds of disk IO. And then about 100 microseconds more of application process. If I speed up the server, percentage-wise, I got very little out of it. The application I/O, the application proceeding had to wait until these I/Os complete. So I couldn't get any more out of it until I could speed that up. If I could now take that 5 milliseconds down to 500 microseconds, I freed up all the CPU resources, the memory that was pinned, waiting for that I/O to complete, and I can get so much more out of my system. Is that a dollar per IOP measure? It's an application I/O dependency that I've turned loose the system. You can prove this by doing a POC, which a lot of people still do. You hate to have to do that because that delays things. But that's exactly where you show this up. I can get thousands of more IOs. I get more out of that application, more out of that server processor, more out of my memory. So this value isn't measured in dollars per gigabyte. Now the dollar per IOP, the misleading thing you get there is what if I took some very large system that had lots of processing power in it, and I didn't say Vmax, and I do the aggregate of the I/O across that, and I could be 1 million IOPS. My dollars per IOP could actually look pretty good. Is that helping this application? Not one bit. So the dollar per IOP and 1 million IOP numbers can be very, very misleading because of this application I/O dependency. And that's why this value of, in this case, solid state, and this was an NAND flash implementation, the value of what it gives you here, by the way, this was from a flash system custom. What it gives you here is in the production it gets out of everything else. The 1,000 transactions per second it brought me. A retailer had a repricing requirement to do every day to set the prices on all their retail and their online goods. They would price that based on demand and cost, and they would run this, and it took 7.5 hours every day to set those prices. They put in 17 solid-state systems, and it takes 30 minutes. It paid for itself in 1 month. Now, could you figure the price out, or the value of that out, without doing a POC? Probably not. But think about this as kind of a gift that keeps on giving. That reduction to 30 minutes means they gained that amount of money every month thereafter. No-brainer. This is a no-brainer. That's why, I talk to people a lot about this. You need to rethink the economics for solid state, and it's not in the storage realm. What we found is the most successful sales that go on for selling solid state is to the business owners, people who own these applications, and the impact it can have on that business. It's not the IT people. We can explain the application I/O dependency to the IT people, but they don't necessarily get the impact on the overall business. So these sales are a little different. They're a higher level sale, a bigger conversation, but they're more impactful. You got to bring the IT people along, and they got to understand it, but the impact on the business is a bigger deal. So what we're starting to see our customers do today is segregate Tier 1 apps in the VMware environments, server virtualization environments, and virtual desktops, and put those on all solid-state systems today, and put everything else on the big systems that they currently have or continue to buy for capacity. But the idea is that I get that type of acceleration, it's worth it to bifurcate my usage for the gains I get. Now that's going to change over time. In the future, we're going to move towards more all solid state, and that's going to take 3 or 4 years to get there. But that's okay. We're going to get there. The big thing is this is an industry inflection point, and the big gains we're seeing in these Tier 1 applications and number of VMs is a big deal. Okay, so now let's talk about optimizing VMs and desktops. Now I said VMware earlier, and not to say anything negative about any of the others, it's just VMware has a bigger share of the market, and for most of our IT clients, it's the one they're most concerned about. But it's true whether they're running KVM or PowerVM or whatever. So the big thing here is to try and drive up the amount virtualized, which has to do with the number of VMs per physical server. Historically, what we've seen is customers typically move their less critical things to virtualized environments first and leave their Tier 1 applications to last, or what we get from some of our clients is over my dead body type of concept. Okay, so the idea is that the critical things, they're very risk averse in dealing with that. But some are being forced into it, and some are trying it, and they're doing it with POCs for the most part, but it's all about driving up the number of VMs per physical. And the goal is to get it nearly 100% virtualized environments. It is a lot of success stories. What we typically see is about somewhere 60-70% virtualized in most of our IT clients, but most of them end up stalling out. And they stall out because of storage bottlenecks. Even if they go out and buy something new, they stall out. So they want to look at new ways to address this. Almost always, it's buying new technology. So benefits there are obvious. I'm going to reduce my capital expenditures. I'm going to reduce my operational expenditures. Have these availabilities to move my workloads around. Getting more reactive. If somebody wants a new server, I can stand it up in minutes rather than days. That's probably the biggest benefit that you don't hear talked about, but it really is a big deal. And then making DR simple. But you end up with this mess here. This mess has to do with, I've got all these different storage systems of different categories here, and I have all these VMs that want to access them. So VMware initially came out and said, let's put in some communications between their system, ESX, and the storage systems to do things faster. So they came out with a bunch in 4.1, a bunch in 5.0 and 5.1, and then of course in about 5 weeks we're going to see another round of these come out. These made a big difference. And these had things to do with locking or copies or whatever. Full copy is a great example. Rather than a normal full copy operation, like I was going to create a new clone of a VM, I would have to go to my storage system and read the data back up into memory, taking processor cycles, locking memory down, and then write it back to the system, again, taking a lot of time. What full copy does says that, hey, storage system, make a complete copy of this data, tell me when you're done. So freed up the processor, let the storage system do that in the background. Very important. Blocking, block zeroing is a great example. Some of the new things that have come along since then. The issue is this made this kind of impact. This impact on the amount of time spent, the amount of memory and CPU processing used, and bandwidth, everything going on here dramatically changed. All because of implementation of capabilities in the storage system to offload that function from the server. It's just a no-brainer. This caused people to rush out and buy new systems that had capabilities to do VAI. And the people that didn't do it, for some reason, hadn't really been told this. So we're going to continue to see these changes occur. And we've seen the first round come out with Windows Server 2012 with Hyper-V. They've added the full copy capability. We're going to see more capabilities come out in these systems. All we're really going to see is the fact that virtual storage, as we define it today, is going to be more effective to help increase the density. And it's almost always going to result in a storage purchase. It's going to be something like a flash system. It's going to be something like a V7000 VAI implemented or a VS8000. Those are going to make a big difference. Virtual desktops, talked about this earlier, it's a bigger problem because what you've got here is a whole lot of virtual machines that really represent individual operating systems. By the way, something like 95% of them are Windows 7, just to give you an example. And then the capabilities to deploy these quickly, cloning of some type. So we see these are the most important factors in storage of VDI, is implementing some type of snapshot capability to very quickly be able to take great cascaded snapshots to clone images. Obviously, thin provisioning, wide striping if it's a disk-based system, and then cache if it's a disk-based system, and tiering. The capabilities are continuing to evolve here. We've got a lot of systems that do layering concepts for the operating systems that you support so they can be updated without having to go back through all of this mechanism. And this is all about how fast can I deliver a virtual desktop. Okay, quick overview on that. Let's talk about archiving. Archiving is one of those things that if you've been in the mainframe world, you've been doing this for a very long time. If you've been doing the open systems world, you probably haven't done it at all. And not a lot of effective tools there. Not a lot of effective or built-in systems to do this. But people are starting to look at the capacity demands that are coming, especially when we're dealing with content repositories. Anybody that's dealing with big data analytics, you know, this has got to be the first thing you look at is how am I going to manage this data that I don't want to get rid of. I've looked at it once, but I want to come back. We were having that conversation about log data. Log data is the poster child for archiving. I can't get rid of it because there's some nuggets in there I may want to look at. I've got to keep it. I want to be able to access it, but it doesn't need to be on this expensive storage I've got. So now we want to look at archiving. One of the things I've been working on recently is doing a research report on the use of object storage and looking at where it applies in the different systems. And the initial focus for object storage is on big data analytics and log data and archiving. And the big thing about object storage, it's a flat namespace, so it can handle billions and billions of objects, whereas most hierarchical file systems tend to fall over when you get several million files in. So archiving is an economic discussion, for the most part. Primarily economics, and it's about putting data that I don't expect to be needed. I don't expect to need any more, or rarely need, on some place that's cheap. Makes a lot of sense, and I did a project for one of the major U.S. banks last year on an archiving strategy, and it was all, I had to end up, I was telling somebody earlier, I had to end up building a TCO model for them to show the economics impact up through 15 years. Because this type of data that you're talking about is kept for decades. And the impact has to be measured in longer periods of time. Because I could make a decision to do something today, it might make sense today, but all of a sudden in 5 or 10 years from now, it's going to cost me a boatload of money to move the data or to change, transform it or something like that. So it's a long-term picture you have to calculate. We also get into the compliance discussion. Kevin and I were talking about a lot of regulations around healthcare, and we do a lot of work in that ourselves, looking at the different capabilities of systems to support regulatory compliance. That tends to be lumped into the archiving environment because almost everybody has some type of data that's subject to some type of rules. If you're in healthcare, if you're in something in pharmaceuticals, even general public businesses have some type of data that's regulated some way. And the times vary widely. And so archiving, you almost always will see a compliance or business governance discussion as well, just because in almost every environment there is some of that data. So this picture works when I talk with customers. I talk about primary storage. Now this is a typical business environment here. The probability of access dramatically drops after about 90 days. If you're in the healthcare industry, that chart's a little different. It's about 1 year. But that scale is there. It's just that the numbers may be slightly different depending on the industry. But in typical business, about 90 days, the inflection point of when I have to access that data has dramatically dropped. Now, if I'm a smart IT guy, I can take that red line and I can use that to my advantage. Knowing what that red line is says, I can handle the data differently. So, when I'm likely to access it, I keep it up with my primary storage. Maybe it is a flash system. Maybe it is my DS8000 or some big system. I also have to bring in part of data management, my data protection policies, and say, this data is changing a lot. So my data protection practices are for highly changing data. But once it moves over here to this low probability of access, I can put this on online storage or archive storage that's accessible. I can move that data there by migration, and I can change my entire protection mechanism because I can only worry about protecting it if it changes. So I'll make my 2 copies, maybe a remote site and a local site, and I never have to do it again for that data because the odds are it's not going to change. All I do then is if there is a change or new data, I make my updates. So I can bring down my operational expense for data protection, change my windows dramatically for data protection. I needed intelligent systems to do that, and I need some policy-based controls about moving the data. I can dramatically drop my storage requirements. And what we typically see, I think I got some examples in here, are savings that are just tremendous. The problem is, and this is the big problem, is this is a project inside of IT of implementing this. It's extra work, probably dealing with systems and software that you don't have or aren't familiar with. That's why we typically see companies like InfoSystems and others go in and actually work with customers to implement things like that. Because it's added work to implement, but the savings are well worth it. Elements in here, primary storage. I've got some software, we call it archiving software, to move the data to an archive-capable storage system, and then obviously make a remote copy of it. That's the type of thing. Keep this picture, keep it simple. Simple is good. Simple allows you to keep some hair. When they get more complex, it's tougher to fight, and there's a tendency over time for things to get complex. So the compliance requirements, most of them are 7 years, some at 10 years for business records, obviously. Some of their basic requirements are authenticity verification and some type of access control, logging of when things are done. So the typical compliance needs are there in the box. I don't need to go through them. But those are the general ones you've got to think about. And secure deletion data destruction is a big part of that. I can't tell you the number of times I've went in and talked to CFOs and CEOs even, and they say, we don't need this data anymore, I want to make sure it's gone. Interesting conversations, but they want that gone. And so it can't be discovered. So a lot of these things here are very common. And you want to look for that capability inside a storage system or an object storage system, whatever. Longevity of data. There's so many people say the default is just keep it forever. I don't know what to do with it, right? And you're saying, well, you're just afraid to make a decision. And they say, yeah, it's my job. So that's why you end up with that a lot. The real problem with that, keeping it forever, is the compounding capacity point. Everybody that sells storage should be very happy. They're just going to keep data and just going to keep building up. But it's a real problem. So what you want to do, from a longevity standpoint, is be able to have systems that automatically can move all the data and all the controls and everything to another generation, transparent. And that's actually one of the biggest discerning factors today. Say, can I move that data around without having to know about it? Another big thing, how do I decide? And if you have to go back to each business owner to make a decision about whether you can archive their data, that's a tough conversation. I've had a lot of those. And the only way you can win that conversation is saying, here's what I'm going to charge you if we do it this way. Here's what I'm going to charge you if we do it that way. If you start the conversation off any other way, you've lost. If you show them the two numbers, then you can win that conversation. But if you go back and say, we want to archive some of your data, you've lost. That's why you have to do the economic calculations first. So these all make perfect sense. And for the most part, it's the date of last access that most people are worried about. You can do things like archive any .mp3 file you find, things like that. Or I always like the example of if you've got somebody you don't particularly care for, any file owned by that guy. That gets archived. So they always have to wait for the data to be recalled if they want it. That'll teach them. They should be nicer. You can also set a lot of exclusions in, like this guy's a pain, but we don't want to really make him mad, so don't do that. Those types of things. But you need those capabilities to select the data under some programmatic control. If you have an archive storage system, you really do need to have a file-based interface because that's what the majority of the data is today. In the future, you're probably going to end up with an API like an S3 or a CDMI capability for object storage. And you want to look at the different systems. Now, there's a lot of systems out there that are designed specifically for archiving. The majority of people that do archiving today, though, are using NAS systems that are hopefully relatively inexpensive. And there are some systems that initially were designed for backup that are being repurposed as archiving systems, like the data domain is a good example. That completely is being recast as an archiving target now rather than a backup device. This is what we recommended for one of our clients here, and we're starting to see this more and more. And it's a two-tier archiving, and what they're doing is they're keeping an online archive that's at a capped capacity point. The worst thing that this customer wanted was to continue to keep coming back every year or every 9 months and buying another system. So they wanted to go in and cap it at a number. Once it got full, they wanted the movement of data off of that system to be based on a capacity threshold. So they could go maybe 5 years without having to do another storage purchase. It made perfect sense. So what we talked about then doing was taking a system here and capping at a particular size, planned for 5 years, and then it would take data and migrate it to a cloud location as its deep archive. If you want to get it back, it's going to take some time, but the data that was sent there was data that hadn't been touched in more than a year or had been identified as closed project data. made perfect sense for them, and it was a great solution. So you could go in there and use either some public cloud or private cloud facilities as your target. In this case, they chose a system that had the capability within that system to migrate data to a cloud location. You can do that within software as well. Something like Enterprise Vault from Symantec has that capability to do a two-tier migration to a cloud location. System-wise, there's a few systems out there that support that capability. Very good solution for that customer. But we think this is going to be probably the primary solution being deployed for the next few years with archiving, because of they get this local under control, manage it, put a cap on it, not have to buy more for it, and then about every 5 years they can completely refresh that. And there's a lot of customers like that. They could continually buying is where they get a little tripped up, saying, I just hadn't planned for the budget for that. The file archiving software is pretty interesting. If you're using, it's data you know you don't need, you can just move it. That's very simple. If it's data in a file system, like with a lot of user data, what you really want to do, and this is the most important part, and people tend to gloss this over, is you want the users to get their own data back without having to interact with IT at all. If they have to interact with IT, they end up doing unnatural things like making copies of their data on USB drives or carving out a disk somewhere else you don't know about and storing data. If they have to interact with IT, they do things differently and try to avoid them. And we find that over and over and over again. So you've got to make it transparent and user-controlled. IT is not involved in it. So typically what we see then are archiving software that will leave a stub or a reparse point or a symbolic link behind in a file system. And if they access the data, it's automatically promoted, transparent to everyone. Certainly there's a log that this happened that nobody needs to know about. And all that happens, if it's in that online archive, is the user may wait a second or two longer. But that's okay. If it's in that offline, it may time out, and you'll get a message saying that you need to wait longer or something like that. But the idea is that it becomes self-service, if you will. Interesting story, I was doing this thing with the bank last year, and they had a separate backup group. And so we started talking about their backups and how many user restores. And it's always harder to get anymore. And I'm thinking, this isn't right. And I asked him, okay, so how does your backup work? And he talked about making all these copies, and he went to 2 different locations, 3 different locations. And I said, so what if the user wants something back? So we've got an online form, they said. How long does it take? He says, oh, about a week. So then we went and checked with a few users. Sure enough, they were making copies of their own data, storing it in their desk drawer, because they couldn't wait a week when they wanted the data back. And they were fat, dumb, and happy, the backup team. They didn't. And quite frankly, if we hadn't talked about it and they kept going on like that, they would have been happy if nobody had ever brought that subject up again. But this is the same thing. You know, if you don't get the users to get it back themselves, you get unnatural behavior. Now here's the bigger part. This is the picture I always sit down and talk to every IT client. It's a simple picture. It's a great discussion. I have my data here. I'm going to make point-in-time copies or snapshots that I can get data back right away. Systems data, user data, and I'm going to maybe do that and keep a week's worth or 2 weeks worth of data copies to get my data back for almost everything to be serviced there. I am going to do my backups. In this case, most environments have some type of governance requirements about making copies of data. And I'm going to do that and push my retained backups as an archive entity. That's a retained backup. But I'm going to use my remote storage for more of my instantaneous recoveries, failover type situations. And this is the picture we talk about all the time. And this is about changing your operational expenses in dealing with capacity increases. I haven't changed my use of backup software at all. I've used it judiciously, but I've changed more towards user-based recovery, either for my local copies or remote copies. And I changed my retained copies, things that I say I need to keep for a year, 2 years, or whatever, to automatically go to an archive system and then put normal expirations on my backup to disk. Tried to make this a whole lot simpler. This is the conversation that goes on for quite a while. You get up on the board, you draw lots of things, and you talk about different pieces of software that fit here. But this is the operational discussion you get into with archiving, because archiving is part of this picture. It's part of data management. And remember, data protection is part of data management. Okay, easy decision. It's all an ROI decision, as a matter of fact. What software you use is actually the most important decision. It's not so much the hardware. Now, let's go into and talk about some of these developments going on here. I think I've got time for this. So, you guys are probably pretty aware of a lot of things coming out. I want to deal with some of the impacts of these things and what's happening. I mentioned object-based storage. Well, object-based storage is all about scale. We look at the information we're starting to retain. And the big issue is information's coming in from non-IT sources. It's log data, it's parametric data that comes from outside, it's social media data. There's all kinds of things coming into IT. Certainly a lot of sensors, it could be video, the things that didn't originate in IT, IT is being asked to store. And that's the most fear-giving element there is inside IT, is somebody coming in and say, oh, I've got this analytics data come in and you've got to store it. And you realize what's coming at you is 3 times more data than you currently have. And oh, by the way, you didn't get much budget to deal with that. And certainly no more people. So people are looking at object-based storage as a scale issue. And it's really about getting a flat namespace to deal with billions and billions of objects. Most file systems have a hierarchical structure. And to traverse the hierarchy, when you start getting over several million files, takes so long that you end up timing out on access, or it's just not adequate. It cannot handle it. And that's why you end up with a flat namespace using object IDs as your key to that. And some object systems allow the indexing to be done in those object systems. Some do not. You have to have your own indexing mechanism for that. The other one is durability. The majority of the object systems being designed today are distributing data across multiple devices or multiple geographies. And distributing the data across multiple geographies gives you the opportunity for geographic-based access plus durability. And most of them are using, I think I'll talk about this in a minute, for error correction, using erasure codes to do that. Most of them use erasure codes, but there are other for error correction technologies that are being used. But that way, you can define protection mechanisms. So the most common is 12 and 16. So I can distribute the data to 16 locations. I only need 12 of them to respond to reconstitute the data. So the durability is a big issue. And cloud access, the majority of the cloud implementations you use today are all using object storage. Anything you do with Amazon, for example, Google, those are all cloud-based. Those are all object-based storage environments. So the new systems out there today, they're real simple. You have, how many people remember mainframe QSAM? Just a few old guys. The 2 primary things you did with QSAM were get and put, right? Guess what the 2 commands you've got to store and read data? Get, put. That's what's object storage is. You have really 4 commands. List, get, put, and delete. And that's the basic commands you have. There's a whole lot been added on to that. Those are the four that are primarily used, and that's what we're using in S3 implementation. That's what they are. So they're very simple. The important part is you can add metadata to this system. Every object has system-level metadata, things that you're familiar with from the file system, like creation date, access controls, and all that. But you can have user or application metadata added to it. And that is where it gets interesting. You can put controls in there like the retention mechanisms, authorizations, identity of who created it. You can put in there things like alerts. If somebody accesses that, who do you alert? You can put that into the metadata in an object system so that you can trigger on lots of different things. It now has gotten very sophisticated. So this is where it gets interesting. The different systems may have limits on the amount of metadata, but not all of it. Now, for those of you that are familiar with file systems, in file systems you have your data and you have your file metadata, and those are stored separately. In object storage, they're stored together. Some of these object storage systems will take that metadata and index it and create a database of information for fast searching, but the real metadata is stored with the file to be processed by an application or something embedded on that object system to do things. It's really interesting. So in object storage, there's a number of different types out here. Most of them have a REST, representational state transfer type protocol API, typically used over Ethernet and HTTP to communicate. They create a global namespace and write the data out as blocks on a storage system, irrespective of what type of storage system it is. It also has, many times, a file systems interface with CIFS, which is now called SMB, or NFS, to work with existing applications. You don't get the rich capabilities of adding more metadata to it, but you can still use it with existing applications. And you have some limit, if you use the file systems, on the number of objects. Whereas in the flat namespace you have here, there's no limit on the number of objects. So what you also have are gateway devices. And you'll hear a lot about these gateway devices. And these are on-ramps to object storage, typically in a cloud location. But object storage can be either cloud-based storage or transparently on-premise storage. And so if you're using Amazon, that's an S3 protocol, you can use one of these object storage systems that supports S3 protocol, and it can be local. So it doesn't have to be a real cloud location. But the idea is that these on-ramps can work seamlessly with existing applications. Typically what these look like are infinite capacity NAS boxes. So there's a number of these on-ramps out there, and they give you a gateway to going to object storage to store billions and billions. This is a big thing here, and this has to do with scale. And we're at the very early stages. Most of you probably haven't been introduced to an object storage system. What we are seeing, let me back up, is a lot of vendors are taking existing NAS boxes and they're adding an object interface on it, but they're mapping everything internally just to another file. And so the metadata is a file and the actual file data is there. And they really are not truly object storage, but they're accommodating the object interface with a NAS system. It's a great half step, but it doesn't get you to the billions and billions scale. But it gets your existing system working like this so that you can deal with an API that's transparent, whether you're talking to a cloud location or to an object storage system. The other thing that's big, important, the technology, and some of you have heard about, is for error correction, primarily with erasure codes. Now these are a big deal because of several things. One is the geographic dispersion I was talking about, and the second one is it's being used in spinning disk storage systems to protect you from these large capacity drives that fail. So the 8 terabyte drives, 6 and 8s are coming out later this year. The problem is, you get a failure in a drive like that, the rebuild time is 4 to 6 weeks. And the probability of a secondary failure, even if you're doing a RAID 6, the probability is really, really high. So consequently, people are looking at protection now to have a selectable protection that's using forward error correction, typically with a Cauchy Reed-Solomon code or God, I forgot the other popular one. It'll come to me. But anyway, a different type of coding system where you decide the protection you want. And so 12 of 16 is the most common. And what you're really doing here, it's a category in computer science called information dispersal. There's a lot of research on this. And you're doing information dispersal to create a code word for data such that you can recover the data with only a smaller number of responders coming back. Erasure codes, some of the vendors keep talking about erasure codes. Erasure code is the algorithm used for forward error correction. And once marketing gets a hold of the name, it's hard to break them with that. Just keep hitting them, it doesn't work. But there's a number of different types of codes. It doesn't have to be an erasure code used for forward error correction. The way this works, in this case here, I did a 12 of 16 example. I have information dispersal coming in, and I'm going to take it and I say I'm going to put it across 16 locations. And I am going to create a code word across that. So I could do it geography-wise. I could send it out to 16 different sites. To get the data back, I only need 12 of them coming back, and I can recreate the data. Now, the key thing about these erasure codes and forward error correction is this is selective. I could do 6 of 9, 12 of 16, 12 of 22. It's all selectable depending on what level of protection you want. It gets a lot more sophisticated, but it's where we go as we get larger capacity drives and we deal with geographic dispersion. This is something we're going to be talking about from now forward. And you're going to hear these algorithms talking about RAID this, RAID that. It's old news. This is what we're going to be talking about for the future. Okay, benefit. This is really interesting. How many of you have heard of the concept of having a sealed disk system where you never replace a drive? You've heard of this, right? IBM had a project called IBM that did this. There's another vendor called XIO that does this. So the idea is that I can do something like put a 12 of 16 algorithm or a 10 of 16 algorithm inside a box and never replace the disk drive if my lifespan is predicted to be something like 5 years. So I just let them fail in place and never replace them as long as I've got enough spares in there and this algorithm works. Pretty cool. That's one of the things that can happen. No service plan. That's a really interesting approach. So, all this stuff's happening today. It's very exciting. Dynamic changes. The big inflection point right now is solid state, and this is from this point forward, it will be different. Now, I'm not saying we won't have spinning disk systems. We will. And we're going to have them out there for the next 7 years, 10 years. But they're going to be used in a different context, primarily in the secondary storage implementation. Our tier 1 applications, the things that are most critical, are going to be on solid state technology, and the economic value it gives you is not something you calculate like $1 per gigabyte. Don't even have that conversation. You've got to talk about what it brings, the economic value. If you have to get down to something, use $1 per IOP, but don't ever talk about $1 per gigabyte, because that means you don't know what's going on here. This is changing the dynamics of what the capabilities are in your environment. $1 per gigabyte will make a lot of sense when you talk about archiving. But that story is only half right. Because in archiving, we're talking about decades. So you really have to do a TCO calculation that looks out probably 30 years in 10-year increments, 10 or 5-year increments, and said, I can deploy this technology. Here's the TCO point at 15 years. And that's what you use to compare against. And that's where this life amplification projects that are going on in some vendors are going to make a whole lot of sense. So you're going to build some economic models, and the dollar per gigabyte, you better stop talking about that because the world's changed. Okay, that's it. Any questions? After it's over, I'll stick around over here for more discussions. Any questions now?
I got a question. The solid state technology is obviously a wonderful solution to electromechanical data storage and data handling. What's next?
Question is, if solid state's a great solution for electromechanical issues, what's next?
And when is it coming?
Let's just say I'll be retired.
I think so.
The horizon is one that's really interesting. Let's think about this. We've got so much data coming at us that the marketing people are out there trying to alarm customers by using things like zettabytes of data that you have to store. That's a whole lot of zeros there. And so they're trying to get people excited about it. There are two factors, three. One, but the biggest one is we got the amount of data coming in that's going to force us into doing some real data management, which we have not done before. We have absolutely stood back and just stored all, just buy more. And with this amount of data, we're going to actually have to manage it a whole lot better. And so we're going to start to see more sophisticated software come in to manage data. That's going to be the first thing we're going to see. And there's nothing that I've seen today that is adequate, in my opinion, but we're going to start to see more. Second thing is we do need to deal with capacities. And so solid state is very effective today, but we're going to see new generations of solid state. Phase change is probably going to be the next one. There'll be another one after that. And phase change is probably deployed about 3 years from now. There are two vendors that are going to deliver phase change first. The first one's IBM, and the second one is a little confusing. It's Micron, but it's Micron licensed to Intel. So those two are going to change the face of that, and it's again 3 to 5 years. There's going to be another solid state technology after that, and I hear 4 or 5 different proposals, none of them which I could say is real. So that's going to be a density issue, density and power, capacity. The last one, which is the one I don't have a good answer for, and I always talk about this, and that's going to be the bandwidth to deliver information. Most people want to be at their homes and have data come fast, and the way it's getting to you now is not near fast enough to deal with the amount of data to be transferred in a few years from now. It just isn't. And so the long pole in the tent is going to be, how do you get data to where you're at? I don't think it's over a while. I don't know the answers. Okay. Next question. Bored, everybody's asleep. Yeah.
You touched on it earlier, but with taking traditional systems and going to replacing spinning drive and solid state, obviously the limitation then becomes the communication bus if you've got a SATA or a SAS communication. Is there any way around that? I mean, are you not using all the capacity of the drive, all the capabilities of the drive you're buying because the bus is looking at you? Okay,
it's a great question. If you plug in SSDs into in place of a disk drive, are you not using all the capabilities of solid state? The answer is absolutely. First thing is, remember, flash memory is a memory access protocol. If you plug it in, use it in an SSD and plug it in place of a disk drive, you're taking a memory protocol and mapping it onto a low-level serial, typically, transfer SCSI. That's what you're getting, serial attached SCSI. So you're doing a handshake protocol for transferring bits back and forth as if it were a spinning disk drive. So that's a command response type of interface rather than a memory address interface. The first thing we're going to see is a change to use a technology called NVMe. How many people have heard of NVMe? That's good. Non-volatile memory enhanced. And so that's going to be a memory access protocol that doesn't use SCSI transfer. So we're going to start seeing that in the next year or two. That's going to be a big deal. But you're also going to see a lot of vendors do their own. Hitachi just came out with a thing called an FMD, and it's a flash module device which they plug in internally into their internal buses. And basically they did their own flash controllers, and they tried to eliminate some of the problems. Basically, the FMDs run about 5 times the speed of an SSD because they've eliminated some of that problem. So that's the type of overhead you see. So the SSDs are a convenient thing to do to fit into existing designs today. A couple of years from now, we'll look at that as really old stuff, and we won't be talking so much about it. The important thing, though, is when you change away from SSDs, what you're using in an SSD is a flash module controller that's a generic controller. You can go into a different type of flash module controller that's custom designed for your application. Remember I talked about these life amplifications to get flash to last 15 or 20 years? Those are with custom flash controllers specifically designed to say that in this usage model, it'll primarily be read-only. As a primarily read-only technology, I can completely change my sparing algorithms, my refresh algorithms, my write algorithms, and I can change the entire economics. And so those are going to come out about 80 cents a gig, if people want to talk about pricing, because of that different flash memory controller. And you won't be able to do that with an SSD, for example, because you're getting more into lower level controller technology. So you're absolutely right. We're not optimizing, and you're going to see the vendors over the next couple of years. Now, if you take the flash system over here, for example, they have their own custom flash controller, and it happens to be implemented in a Power PC. But they can get more sophisticated. That's where you can go into that and add in your own compression algorithm, for example, or data reduction algorithms. So you can get, when you start putting that into that flash controller, you can move yourself a long way forward compared to using something that looks like a disk drive. Yeah.
How is this going to, with flash and solid state, how is that going to affect bandwidth and back-end infrastructure around like, fiber channel or high SCSI?
So what's the interface protocols? What's the effect of flash going to be? That's an absolutely great question. We've got guys from QLogic and Brocade here, so you guys are going to have to step up and talk about this. But this new Gen 5 technology coming out, which everybody talks about as 16 gigabits per second, but it's more important than that. It actually has a lot of latency reduction. So that's where it's going to really drive the delivery of flash systems that support Gen 5 technology are going to drive an infrastructure change to that Gen 5 technology. They are really going to push an infrastructure switchover to reduce that overhead to get down to that sub 100 microseconds response time. Remember that example I showed you, what the effect of reducing that response time has on transactions? It's going to be justified. What we typically see is the iSCSI is relegated primarily down market today, and the higher performance systems don't typically have iSCSI on them. They're going to have InfiniBand or fiber channel. You'll see a lot of solid state systems with iSCSI on them, but they're not at the same performance level as something like this. So I think you're going to see a big boom in switch over to the Gen 5 fiber channel technology. And then the next iteration of that, I think it'll be accelerated because of that. So, guys like Brocade and QLogic should be real happy. Yeah.
Some of what you said was about some of that transition is the PCIe Gen 3, which is on the class of those or the faster access time, so it'll give that to you. But you did make a point in your presentation about the PCIe Gen or the PCIe product and a flash today, and you mentioned that there was not a sharing way to share between those. And there is one company that does have a flash product out there that does share between between it in a clustered environment with completely transparent to the customer.
That requires an external connection.
You have to be tied into, you've got to be in a clustered environment. But as long as you're in a clustered environment, you can't share.
Yeah.
That's pretty key.
Yeah, yeah. But it
I don't know
requires.
if you're aware of that, not aware.
Oh, no, from day one, I was aware of Mount Muir.
Okay.
Yeah, but it is software that's running internally that requires an external connection to do that.
Right, but they can't share between the clusters.
Right.
Between the servers, yeah.
Mhm. Okay, any other commercials?
I love it.
So, any more questions? If not, oh, go ahead.
As we start to introduce solid state into the environment, is it going to enhance the need for moving to faster networks or even converged networks? Because in many cases, most of the clients I see today are still working on 1 gig infrastructures.
Oh, yeah, it's going to force that because you're not going to get the benefit unless you really move up. And so I think it's going to move. The majority of the people I deal with in the Fortune 1000s are at 8s, and they're going to move to the Gen 5. And in the mid-tier, I most of the time see 4 as the fiber channel, but I see a lot of them were contemplating the move to FCE, and they're not going to do that.